Have you ever tried to put your right glove on your left hand? It just doesn't fit, does it? That's because your hands are a perfect example of something scientists call chirality. The word chiral comes from the Greek word for hand, care. It describes an object that cannot be perfectly lined up with its own mirror image. Think about it. Your left hand is a mirror image of your right hand, but no matter how you twist or turn them, you can't make them identical. They are non-superimposable mirror images. This simple yet profound idea is all around us, often hiding in plain sight, from the very molecules that make up our bodies to the grand spirals of distant galaxies. It's a fundamental property of geometry that shapes our world in ways we are only just beginning to fully understand. Chirality is nature's signature move. Many of the building blocks of life itself are chiral. The amino acids that link together to form proteins in our bodies are almost all left-handed. On the other hand, the sugars, like the ones that form our DNA, are almost all right-handed. This isn't just a random choice. It's essential for life to work. Imagine trying to build a complex machine with screws that have different threads. It would be a mess. Life's machinery depends on using consistently shaped parts. This is why a right-handed medicine might cure you, while its left-handed mirror image molecule could be completely ineffective or even harmful. Nature's preference for one hand over the other is one of science's most fascinating and enduring mysteries. You can find chirality in the world all around you if you know where to look. Take a walk outside and observe the climbing vines of a morning glory plant. They almost always spiral in the same direction. Look closely at the beautiful swirling shells you might find on a beach. They too have a specific handedness, a direction to their twist. Even on a subatomic level, some particles exhibit a form of chirality. This property isn't just a fun fact. It has huge implications. Understanding how nature uses handedness helps us design better drugs, create new materials, and even search for life on other planets. By studying these natural examples, we can learn the rules that govern our universe. So why does this handedness matter so much? It all comes down to interaction. Just like a right hand fits best into a right-handed glove, molecules need to have the correct shape to interact properly with each other. In biology, this is called molecular recognition. An enzyme, which is a type of protein, might have an active site shaped to fit only a left-handed molecule, completely ignoring its right-handed twin. This selectivity is the key to everything from how we smell a rose to how our bodies process food. This fundamental principle of shape and fit is not just important for nature. It's a tool that scientists and engineers are now using to build the amazing technologies of the future. Now let's talk about building things. Usually when we make something, we are limited by the properties of the materials we find in nature, like wood, metal, or plastic. But what if we could design materials to have any property we wanted? What if we could tell a material exactly how to behave? This is the incredible idea behind metamaterials. The prefix meta means beyond, so metamaterials are substances that go beyond the properties of their natural components. They are artificial structures engineered on a tiny scale, often smaller than the wavelength of light, to do things that ordinary materials simply can't. They are like Legos for scientists, allowing us to construct materials with extraordinary abilities. Instead of relying on chemistry, metamaterials get their amazing properties from their structure. Imagine building a wall not out of solid bricks, but out of billions of tiny, intricately shaped antennas or resonators. The overall effect of these tiny structures working together is what gives the metamaterial its power. By carefully designing the shape, size, and arrangement of these tiny building blocks, scientists can control how the material interacts with energy waves like light or sound. This allows them to create things that were once thought to be pure science fiction, such as invisibility cloaks that can bend light around an object, or super lenses that can see details smaller than a wavelength of light. So, what happens when we combine the idea of chirality with these amazing metamaterials? We get chiral metamaterials. These are special materials engineered not just to interact with light, but to interact with its handedness, or what scientists call its polarization. Light waves can wiggle in different directions as they travel, and some light, called circularly polarized light, actually spirals like a corkscrew as it moves. This spiraling light can be either right-handed or left-handed. Chiral metamaterials are designed with tiny, twisted structures, like microscopic springs or helices, that are incredibly sensitive to the handedness of light. They can interact very differently with left-handed light compared to right-handed light. This unique ability to sort, filter, or manipulate light based on its chirality is what makes these materials so special. A normal piece of glass treats left-handed and right-handed light exactly the same, but a slab of Chiral metamaterial could, for example, completely absorb all left-handed light while letting all right-handed light pass through perfectly. Or it could twist the polarization of light to an extreme degree, far more than any natural material. This gives us an unprecedented level of control over the most fundamental properties of light. By designing these materials, we are essentially writing new rules for how light and matter can interact, opening up a whole new world of technological possibilities. The story of chirality didn't begin with advanced labs and powerful microscopes. It started over 200 years ago with curious scientists observing the world around them. In 1811, the French physicist Jean-Baptiste Biot discovered that when he shone polarized light through certain natural substances, like quartz crystals or sugar solutions, the light's polarization would actually rotate. Some substances rotated it to the left, while others rotated it to the right. He called this phenomenon optical activity, but he didn't know why it was happening. He had stumbled upon the macroscopic effect of molecular chirality, a clue to a hidden world of handedness that would take decades to fully uncover. His work laid the foundation for a whole new field of study. The next giant leap came from the brilliant French chemist and microbiologist Louis Pasteur. In 1848, Pasteur was studying tartaric acid, a chemical compound found in wine sediment. He noticed something strange. There were two types of crystals that were mirror images of each other, like a pair of tiny left and right hands. Using a pair of tweezers and a microscope, he painstakingly separated the left-handed and right-handed crystals into two piles. When he dissolved each pile in water and shone polarized light through the solutions, he found that one solution rotated light to the left and the other rotated it to the right. He had proven that chirality at the molecular level was the cause of Biot's optical activity. Pasteur's discovery was monumental. It connected the visible shape of a crystal to the invisible, three-dimensional shape of its molecules. He famously proclaimed, "The universe is an asymmetrical entity." This idea was further explored by the great physicist Lord Kelvin, who, in 1884, formally coined the term chiral to describe this property of handedness. Kelvin understood that this concept of shape and symmetry was fundamental, applying not just to chemistry, but to physics and mathematics as well. These early pioneers, working with simple tools but brilliant minds, peeled back the first layer of a deep scientific mystery, setting the stage for the modern era of material science. For a long time, our ability to manipulate chirality was limited to what we could find in nature, or create through complex chemical reactions. But the development of metamaterials in the late 20th century changed everything. Scientists were no longer just observers of chirality, they could become its architects. They realized they could design artificial structures with a handedness far stronger than anything found in nature. By creating arrays of tiny metal helices or other twisted shapes, they could build materials that had an incredibly powerful interaction with polarized light. This marked the beginning of a new chapter, transforming a historical curiosity into a cutting-edge field of technology. So, how do we actually build these incredible Chiral metamaterials? The answer lies in the amazing technologies of the 21st century. To control light, the building blocks of our metamaterials need to be smaller than the wavelength of light itself. For visible light, this means we need to build structures that are just nanometers in size. That's a billionth of a meter. This is made possible by techniques like electron beam lithography, which uses a focused beam of electrons to draw patterns onto a surface, or advanced forms of three-dimensional printing that can build complex, three-dimensional shapes on a microscopic scale. These tools give us the power to design and construct chiral structures with mind-boggling precision. The ability to manufacture these materials is a game changer because it allows us to customize their properties for specific tasks. Do we need a material that strongly absorbs right-handed light but reflects left-handed light? We can design a metamaterial for that. Do we need a sensor that can detect the presence of specific chiral molecules, like those found in certain diseases or pollutants? We can build a chiral metasurface to do just that. This move from discovering materials to designing them is a massive leap forward. It means we can create solutions to problems that were once unsolvable, simply by engineering matter at the nanoscale to behave in entirely new ways. The potential applications for Chiral Metamaterials and the meta devices built from them are vast and exciting. In telecommunications, they could lead to new types of optical fibers and antennas that can send more information more securely by using the polarization of light as an extra channel for data. In medicine, they could be used to create highly sensitive biosensors that can detect diseases at their earliest stages by identifying chiral biomarkers. They could even improve solar cells by trapping more light or lead to new kinds of ultra-thin, high-performance camera lenses. We are on the verge of creating a new generation of technology powered by these smart, structured materials. The journey from observing a strange property in a sugar solution to designing and building Chiral metamaterials is a perfect example of how science works. It's a story of curiosity, brilliant insights, and technological progress building on each other over centuries. As we continue to unlock the secrets of chirality and master the art of building metamaterials, we are opening doors to a future that is smarter, safer, and more efficient. The world around us is full of handedness, and by learning to speak its language, we are not just understanding the universe better, we are learning how to build a better one. Consider the possibilities. They are, quite simply, awesome.